Welcome, my friends, to my YouTube channel. Now, yesterday I have already give the introduction of entropy and also discuss few important properties of entropy. Uh, okay, now today I shall discuss few other properties of entropy and few other issues. Okay. So entropy is a perfect differential and it is also a single valued state function that we discussed in our previous lecture. And also we see that it is a measure of disorder of a system or randomness of a system. And another thing that another property is that we all know that work is nothing but due to the ordered motion of the molecules of a system. Okay, work is due to the ordered motion of the particles. Okay, and entropy is a measure of disorder. So from these two we can easily conclude that entropy is a measure of unavailable energy or work. Okay, so how? So we all know that work is due to the ordered motion of particles. This is one. So ordered motion, regular motion, but entropy is a measure of disorder. What is entropy? Entropy is a measure of disorder. So these are opposite. One is ordered motion and another is due to disorder or randomness. So that means it is a measure of unavailable energy or work. Okay. So we can conclude that entropy is a measure of unavailable energy of a system, unavailable energy or work, whatever you can say, unavailable energy or work. Okay, now later we will explain it more accurately by taking a suitable example. Later I also discuss it about it by taking a suitable example. So we all know that work is due to the ordered motion of the particles and entropy is a measure of disorder. So clearly it is a measure of unavailable energy of a system. So this is one property. And another property that entropy and probability, there is a connection between them. And we all know that entropy is nothing but the product of Boltzmann constant and the log of thermodynamic probability. So we can explain it later. So what is thermodynamic probability and what is the difference between thermodynamic probability and mathematical probability, that we will discuss in later. But now you know that there is a connection between entropy and thermodynamic probability by this relation. Okay, where we have to mention that W is thermodynamic probability, not the mathematical. Thermodynamic probability. Okay, thermodynamic probability. So these are the two important properties, two other important properties that I have to tell. Okay, now let us come to another issue. Now I have started the entropy by using the concept of second law of thermodynamics. Okay, let us try to find out the concept of entropy in a more general way, and let's check whether it is agreed with the second law or not. Okay, so we will going to discuss the concept of entropy in another way, and let's check whether it agrees with second law or not. Okay, so just take the PV diagram, that is the PV indicator diagram. Okay, just take the PV diagram, and here just you consider two Carnot cycles. Give it a name A, B, C, D, and the second one is EF. Okay, so here there are say this is T1, T2, T3. So here this diagram consists of two Carnot cycle. So first one is ABCD cycle. This is the ABCD cycle. Okay, so just take the first one. So what happens in case of a first cycle? The engine absorbs heat say at temperature T1 and rejects it to sink at temperature T2. Say for the first cycle, Q1 heat is absorbed from the source at temperature T1 and Q2 is the heat rejected to sink at temperature T2. So what happened in case of a reversible Carnot engine, that we already know. We need not to require the proof again, that we already know. So Q1 upon Q2, this is equal to T1 upon T2. So what we get, that is Q1 upon T1, this is Q2 upon T2. Give it a name. So this we can write for a first Carnot engine or Carnot cycle. Now if we take the second cycle C, D, E, F, then this cycle absorbs that amount of heat which was rejected by the previous one. That is, it absorbs heat Q2 and rejects heat Q3. Okay. Several Carnot engines. So the second one absorbs that amount of heat which was rejected by the previous one. Okay. So what we can write for the CDEF cycle, what we can write in this case, similarly we can write Q2 by Q3 equals to T2 by T3. So from which Q2 upon T2, this is equal to Q3 upon T3. So give it a name, say 2. So what we conclude from these two diagrams, we conclude that Q1 upon T1, this equals to Q2 upon T2, Q3 upon T3 remains constant. So this remains constant. Okay, or more in general, what you can say, in general you can say Q upon T is constant. Okay, so this is nothing but the entropy. In general we can say, again we see that Q up by T, this is constant, and what is it? This is the dimension of entropy. And instead of Q amount of heat, if you take dQ amount of heat that is absorbed at temperature T, then you can write the entropy as ds. Okay, that you can write the entropy as ds. I can write here. So here Q by T means the Q amount of heat is absorbed at temperature T. Okay, so instead of Q, if dQ amount of heat is absorbed from the source at temperature T, then what will be the increase in entropy? That is ds. So what will be S in this case? That is line integral dQ upon T. So again we see that this definition agrees with the previous definition that I told during the adiabatic process when there is no exchange of heats. Okay, so this gives the definition of entropy. Okay, so thus we see that by considering the Carnot cycle PV diagram, the concept of entropy is also become right. That means it agrees with the previous definition. Okay, so this is the one thing. Now another thing that I am going to discuss is that what will be the change of entropy in reversible and irreversible processes. So one thing I forgot to told, what is reversible and irreversible process, that I told in the next lecture, because now I have to show this. So in my next lecture I will tell you what is irreversible and irreversible process, what is spontaneous process, that I will discuss in my next lecture. Okay, that I forgot to tell. So change in entropy for a reversible process. Reversible process means the process that can be retraced in the opposite direction, so that the working substance can undergo the same amount of change as it does in the direct process, right? The reversible process means starting from a particular point, if a system can reach the initial point again, okay, or that it can be retraced in the opposite direction, that I tell, okay, that I can explain in next class more accurately. So now you know that reversible process is one that process can be retraced in the opposite direction, okay, so that all the steps follows in direct process can also be followed in the backward process. That means can be retraced in the opposite direction, so that the substance can follow the same conditions as it does in the direct process. That is reversible process. We will explain it later. So what will be the change in entropy for a reversible process? So take a example. Suppose a system moves from here to here, that is from A to B, and again returns from B to A, okay. So suppose it moves from A to B via ACB path and returns from B to A via BDA path. So this is a reversible cycle. A, C, B, D, A. Why? A, that is initial and final, again returns to the initial state, is reversible. Okay, this is reversible. So what will be the change in entropy in going from A to B? We know the formula, ds equals to dq by t. So what will be the change in entropy in going from A to B? Integrate it over A to B. That is ds. You can integrate it over A to B. This gives dq upon t. So what will be the result? My result will be, say, SB. And SA are the initial and final entropy. So this must be equal to A to B dq by t. Okay. So this gives a name, say 1. So this is the change in entropy in going from A to B via ACB path. Okay. So via ACB path. Now what will be the change in entropy in returning from B to A via BDA path? What will be the change in entropy in returning from B to A via BDA path? Okay, so returning from B to A, that means A is final and B is initial. So in this case, B to A will be the limit. So this gives B to A dq upon t. So clearly the result is SA minus SB. So this is B to A dq upon t. Now you can find out the total change in entropy in the full cycle by adding these two. Okay, so the result will be 0. Okay, so what will be the total change in entropy? So for the whole cycle, for the entire cycle, so what will be the change in entropy? The change in entropy will be what? So A to B, this is dq upon t, plus B to A dq upon t. And what we get? This we get SB minus SA, and that we get SA minus SB. So this cancels, so this becomes 0. So what is this? A to B, B to A, entire cycle, that you can write in this way. So line integral dq by t, this is 0. So this is the dimension of entropy, or is a measure of entropy. So for a reversible cycle, we clearly see that the change in entropy is 0. Just you think this simple diagram, you need not to consider a critical diagram. Just you draw a simple diagram and you can easily check it by considering that diagram. You need not to consider any critical diagram or a complex diagram. Okay, this diagram is sufficient to check it. So we have shown the change in entropy for a reversible cycle is 0 by considering a suitable simple diagram. Okay, now let's check what will be the result in case of a irreversible process. An irreversible process is one that cannot be retraced in the opposite direction. Okay, and maximum processes that are occurring in nature are irreversible. Okay, so almost 99% processes are irreversible. So this process cannot be retraced in the opposite direction. Okay, and for example you can say Joule-Thomson effect that we will study later. Say current flows through a resistance, this is also irreversible Joule heat loss. So these are the examples: Joule-Kelvin effect, or current flowing through a resistance, that is when heat is produced, I square RT. So these are the examples of irreversible processes. Okay, so that we will discuss in our next class. So what happened in case of a irreversible process? So let's check. The process is irreversible. Now here we have previously discussed that the efficiency of a Carnot engine working between the temperature limits, reversible Carnot engine working between the uh, two temperatures, say T1 and T2 is what? 1 minus T2 by T1. Here R means the engine is reversible. Okay, so we take a reversible engine working between the two temperature limits T1 and T2. The efficiency can be written in this way. Now what will be the efficiency of an irreversible engine working between same two temperature limits? That you can write 1 minus Q2 by Q1. Okay, 1 minus Q2 by Q1 is a general formula, but for reversible engine you can express Q2 by Q1 in terms of T2 by T1. But for irreversible process or irreversible engine, you can't express Q2 by Q1 in terms of T2 by T1. So remember this thing. So this is the general expression for the efficiency of a irreversible engine. Okay, working between the same two temperature limits. Now by using Carnot theorem, which we will study later, Carnot theorem, just I tell that, states that no engine is more efficient than a reversible engine. That means reversible engine have the maximum efficiency and no other engine can cross it. So from Carnot theorem that we learn later, from Carnot theorem, what we get? Eta R, reversible engine is efficiency is greater than the efficiency of irreversible engine. So what will be my eta R? 1 minus T2 upon T1. This greater than 1 minus Q2 upon Q1. So minus T2 by T1 is greater than minus Q2 upon Q1. So if you change the sign, then it will become opposite. So Q2 by Q1 is greater than T2 by T1. So what we get? Q2 upon T2 is greater than Q1 upon T1. So this is what? This is the final entropy and this is the initial entropy. So what will be the result? The result will be positive, that is greater than 0. Oh sorry, not equal, that will be positive. So by using Carnot theorem, we can clearly check the final entropy is greater than the initial entropy. That means change in entropy is positive. So what does it indicates? That efficiency in case of irreversible process increases. As I told previously that the entropy of the universe is increasing. So what, these are identical. Okay, just since all the processes occurring in nature are irreversible, so the entropy of the universe is increasing. Okay, so all processes occurring in nature are irreversible. Okay, so entropy increases. So S say increases. So we can say entropy of the universe is increasing. Okay, so this we can see that entropy of the universe increasing, since the process is irreversible and all processes occurring in nature are irreversible. We can say the entropy of the universe is increasing. Okay, so in our next class we will discuss few other issues related to entropy, and I have to mention the reversible and irreversible and spontaneous processes. Okay, so this is what about today. So if you don't subscribe my channel, then kindly subscribe it to get latest videos on higher secondary and BSc physics. Okay, thank you.